Alrighty everybody, set 9.1 stoichiometry. This is the section that gave the most students trouble in regular chemistry. I'm sure many of you guys remember this evil S word. It's all about counting by weighing and then using mathematical relationships to figure out how much of a yield you can get out of a reaction. In essence, it really isn't all that difficult. It's just multiplying four fractions together, but the setup is where most people get really confused. So we're going to break this up into two sections. 9.1 stoichiometry, 9.2 stoichiometry continued. Let's begin with the basics. Avogadro's number. That is equal to 6.022 times 10 to the 23rd power. This should look rather familiar to you people that have already been in chemistry. If you're wondering what that number looks like written out, there it is right there. 6.022 with 20 zeros after it. That number is so large that, one, I don't even know how to say it, and two, if you tried to count to that number, it would take you forever. I mean, you wouldn't be able to do this in your lifetime. You wouldn't be able to count to that number in 100 lifetimes. It is so large. If you had 1 mole of pennies, it would wrap around the world several times. That's what I'm told by one of my college professors. So let's go into this. Avogadro's number, 6.022 times 10 to the 23rd. This is a counting number, ladies and gents. Just like 1 dozen is equal to 12 things, 1 pair is equal to 2 things, 1 triplet is equal to 3 things, 6.022 times 10 to the 23rd things is 1 mole. Okay? This unit right here, the mole, is the chemist's dozen. Just like 12 things is the baker's dozen, chemists use the mole. So if you have 1 mole of anything on this planet, you have 6.022 times 10 to the 23rd things. If you have 1 mole of hairs I should say, you have 6.022 times 10 to the 23rd hairs. If you have 1 mole of shoes, you have 6.022 times 10 to the 23rd shoes. So forth and so on. It is a counting number, ladies and gents. Because this number is so large, or before I get to that, it's just simply a counting number, like triple, pair, dozen, quadruples, so forth and so on. So just to reiterate, 1 mole of anything on this planet is 6.022 times 10 to the 23rd. Alright? If you have 1 mole of something, then whatever mass that thing has is known as the molar mass. Now, I forgot to go over this in set 1, but mass is another unit of measure, and it is equal, or it has the units of grams. Okay? We measure it in grams. So 1 mole of something, whatever that thing weighs out on a scale, we call it the molar mass. You can figure out the molar mass of any element on the periodic table just by looking at the periodic table. Let's take Na, for instance, sodium. Sodium is one of our alkali metals. There it is right there, number 11. If you want to find the molar mass of an element, it's right there. Its average atomic mass. Okay? So 1 mole of sodium weighs 22.99 grams per mole. That is the molar mass of sodium. Let's just say for giggles, what's the molar mass of carbon? Well, let's look at carbon here. It's number 6 on the periodic table. There it is right there. Carbon weighs 12.01 grams per mole. So if you have 1 mole of carbon, if you have 6.022 times 10 to the 23rd atoms of carbon, it will weigh 12.01 grams per mole. In chemistry, we have to count the number of things we have by weighing them because atoms are so small. It's kind of like going to those family fun centers when you get all those tickets. They put them in a bowl and they weigh it, and it tells you how many tickets you got. Let's figure out the molar mass of a compound. It's a little bit more complicated. Let's take iron 3 oxide here. Okay? You should know by now that this is iron 3 oxide because oxide has a negative 1 charge. There's 3 of them, so iron has to have a 3+ charge to balance it out. So how do I figure out the molar mass of a compound? Well, it's very simple. Let's make a list of all the different types of elements we have here. We have iron to begin with. We have an oxygen, and we have a hydrogen. All right. How many ions are in this formula right here? If you said 1, you are 100% correct. There is 1 iron in this formula. This 3 on the outside of the OH does not apply to this iron. There's an imaginary 1 here. How many oxygens are in this formula? If you said 3, you are 100% correct. Because we have to multiply all the individual numbers on the inside here by the number on the outside. There's an imaginary 1 with this oxygen and an imaginary 1 with this hydrogen. But they are grouped together by a bond, and in fact they are grouped together in 3s. So 1 or 3 times 1 are 3 total oxygens. Same thing with the hydrogen. 3 times the 1 hydrogen, 3 total hydrogens. So counting the atoms is the beginning portion of getting the molar mass. Now we need to actually go through and get their individual masses to determine what this whole thing weighs. Let us start with iron. Iron on the periodic table, it's one of our transition metals. Right there, he has a weight of 55.85 grams per mole. I'm going to go ahead and leave off the unit just for now. Wait till the end, it makes life a lot easier. Oxygen is next. Oxygen weighs 16. So we're going to have 3 times 16. Hydrogen weighs 1.01. And now I go through and multiply. 1 times 55.85 is just 55.85. You can do this next one in your calculator, but I can do it in my head. 3 times 16 is 48. And then 3 times 1.01, again, you can do it in your calculator if you need to, but I can do it in my head. It's 3.03. And once you have all the individual masses of each of the elements, you can add them all together to get a total. Now, how many significant figures are we going to be allowed in this answer? We should end up with a total of 4. 2 after the decimal, and then 2 over here. Actually, we're going to end up with 5 because this is going to come out to be more than 100. But after the decimal place, we were allowed 2 places because each one of these has 2. So if we add this together, I'll go ahead and do this one in the calculator for you guys. Oops, didn't end that. $106.88 grams per mole. Okay, you got to tack on that unit for molar mass. Okay, so 1 mole of FeOH3 weighs 106.88 grams per mole. 1 mole of sodium weighs 22.99 grams per mole. You should be able to go through and calculate the example problems that I left for you in the summer assignment now. Plus, this is a review. This is a review right here. Okay. This last portion, before we move on to 9.2, we didn't do it this year in chemistry, but last year in chemistry we did do it a little bit. If I'm given, 2 moles of beryllium, how many atoms will I have? This is a dimensional analysis question, a special type of dimensional analysis question known as stoichiometry. So we were given 2 moles of beryllium. The question wants us to find how many atoms total will I have. Well, think about this. If I have 1 dozen things, then I have 12 things. How many things do I have if I have 2 dozen? Obviously 24, correct? Well, if I have 1 mole of something, then I have 6.022 times 10 to the 23rd of whatever that thing is. If I have 2 moles, then I have double this number. Just like if I have 2 dozen things, then I have double the number of things. 2 dozen is 12, or 2 dozen is 24. 1 mole is double this number, which I don't know. We'll have to plug this one into a calculator. But let's set it up first. We have 2 moles. I abbreviate mole, MOL. I know it's not much of an abbreviation. Of beryllium. We have to multiply that by a conversion factor, and our conversion factor is 1 mole is equal to 6.022 times 10 to the 23rd. In this case, we're dealing with atoms this time, okay? Because it's asking for atoms. I want to cancel this mole of beryllium, so I must have mole of beryllium down here. That'll leave me with atoms up top, which is what we're looking for. This number is 1, because 1 mole of beryllium is equal to 6.022 times 10 to the 23rd things. Now let's plug that into our calculator. 2 times 6.022 exponent 23rd. By hitting this exp here, it automatically tells the calculator times 10, and then we plug in the exponent 23. We plug this in. We are given 1.2. Ooh, this is a good question. This is a definition right here. This is a definition. This is a number that we were given. How many significant figures am I allowed in this answer? We're only allowed 1. Definitions don't count, and there was only 1 number right here. So we're actually going to have to round this off to 1 significant figure. Okay? Here's our 1 significant figure. It's next to a 2, so 2 is going to just keep that down to 1 times 10 to the 24th power. Okay? The space in between indicates times 10, and then there's the exponent to the 24th power. Very good. Alrighty, that's all I have for you for 9.1. Stay tuned for 9.2.